The paper we're diving into today is Low-Cost Experiment to the Correct Relativistic Energy Formula by David Lush. Bit of a mouthful, but honestly, the questions it raises are pretty fascinating.
Yeah, this one really made me sit up. Basically, Lush asks, hey, what if the formula we all use for relativistic energy, Einstein's famous E equals mc squared thing, isn't actually the most fundamental version? Like, what if there's another valid formula that works just as well, or maybe better in certain contexts?
Right. And in this paper, Lush compares Einstein's version with an alternative that's been proposed by Osiak. So the big question he's trying to settle is, which relativistic energy equation actually reflects physical reality? I mean, no big deal. Just trying to overturn 100 years of physics.
Yeah, small potatoes. But seriously, the significance here is huge, right? This basically gets right to the foundation of modern physics. If our main energy equation is off, even slightly, it might ripple out into how we understand everything from particle physics to cosmology. Stuff like dark energy, inflation, even dark matter.
Exactly. The alternative formula comes from Osiak's idea, which is built not from Einstein's 3D Planck equation, but from integrating the Minkowski equation, the four-dimensional approach. And Osiak's version actually gives a rest energy that's half of Einstein's. So instead of E0 mc squared, you get E0 equals mc squared over 2.
Yeah, and for moving particles, the formula is even more wild. It becomes E equals gamma squared mc squared over 2. So it's quadratic in the Lorentz factor gamma, not linear like the standard E equals gamma mc squared.
Here's a quirky thing, though. Osiak's formula lets gamma, the Lorentz factor, be negative, without invoking any of those weird negative energy states that give physicists nightmares. That opens up whole new interpretations for antimatter and time symmetry.
Which is kind of trippy. But Lush points out there's a downside to Osiak's approach. It doesn't conserve energy in relativistic particle collisions. Apparently, that's the main reason Einstein's version became standard. It's the only one that keeps energy conserved when things are moving really fast.
True, but Lush argues that energy non-conservation might actually be a feature, not a bug. He ties it into all these weird cosmological observations, like why the universe is expanding faster than expected, or why dark energy might exist at all.
I liked how the paper keeps circling back to experiments. Lush proposes a clever, low-cost experiment using standard pair creation, shooting gamma rays at heavy nuclei to create electron-positron pairs. The idea is to check if the positron literally appears after the event, as standard theory predicts, or if it could be detected before, according to Osiak's framework.
The thing that jumped out at me, if Osiak's right, positrons, which are like time-reversed electrons, might actually be detectable before they're created in the lab frame. That's wild. Like actually probing the nature of time with a particle detector.
Yeah, it starts getting into that realm where physics feels more like science fiction. But Lush provides practical tests. Look for time advances in positron detection, compare trajectories in magnetic fields, actual empirical ways to distinguish between theories.
And he brings up this whole thing about how changing the energy formula might explain the missing mass in galactic rotation curves, classic dark matter problem, without needing some new particle. If you double the energy in certain collisions, you might account for that extra gravity.
Right, though, I have to admit, there's a part of me that gets suspicious here. Like, physics is full of people dreaming up alternative models that try to explain away dark matter or dark energy.
Yeah, totally. And honestly, not all of them hold up when the data comes in. But I think Lush's point is less about saying Einstein is wrong and more that science should keep pushing at the boundaries and not rule out alternatives just because they don't fit the current narrative.
There's also this side digression in the paper about preons, remember? Like, what if quarks and leptons are made of even smaller bits? It doesn't totally flow with the energy experiments, but I guess it's all part of asking, what's really fundamental?
Yeah, I kind of lost the thread there for a minute. But the upshot of the whole paper is, let's not treat equations as gospel. Physics progresses when we're open to experiments that could shake the bedrock. I mean, we might not end up upending E equals mc squared, but even asking the question can tell us a lot.
Couldn't agree more. Even if this alternative formula doesn't pan out, trying to prove, or disprove, it pushes the precision of what we know.
Welcome back to another episode of In Depth with Academia. I'm Richard Price, CEO of academia.edu. And, well, today we're really diving into something wild. We've got a paper by David Lush, and let me just say it's called On Einstein, Minkowski, Osiak Relativity. And oof, it's a doozy. Just a quick note before we start. I'll be presenting the paper's ideas neutrally. I'm not endorsing them or taking sides here, so keep that in mind. Academic research is always an exploration, not some kind of ultimate truth or finished story, right? All right, so what's this paper actually about? The core question is all about energy and relativity, and whether the way we currently calculate things like rest energy and kinetic energy in particle physics might actually be off the mark. The author builds on ideas from a guy named Osiak, and he asks, what if instead of the famous E y mc squared that's like plastered all over science textbooks, the true formula for rest energy is actually E mc squared divided by 2. That is E mc2 ho, right? If you remember your high school physics, or even if you don't, you probably know that E mc2 feels like one of those ironclad laws of the universe. But David's saying, well, maybe not. And here's why this matters. If those alternate formulas are right, then, well, the universe might not actually conserve energy in the way we expect, especially in high-speed or relativistic collisions between particles. That's huge because energy conservation is like one of the most sacred cows in science. Take that away, and wow, everything feels up for grabs. Also, this might potentially explain things like dark energy or dark matter, those mysterious phenomena that seem to be causing the universe to expand faster and, like, holding galaxies together even though we can't see what's doing it. Wild, right? So, how does David Lush get there? What's the paper's main approach? He shifts from the usual way physicists describe particle motion using so-called Planck equations to focusing on fully four-dimensional equations based on Minkowski space. Hang on, quick digression. Have you ever noticed how Minkowski makes it sound like we're talking spy novels or something? Honestly, someday someone needs to write Minkowski, space-time, detective. Sorry, back to the science. The point is, Minkowski's four-dimensional equations treat time and space on the same footing, rather than splitting off time as kind of an afterthought. Anyway, by using these more covariant equations, David gets some results that clash dramatically with what we see in, say, particle accelerators or our old friend Einstein's relativity, for example. He says that instead of E mc2 for rest energy, it's actually half that. Similarly, instead of traditional formulas for total and kinetic energy, we get E g2 mc2 2 and kinetic energy as p2 notuium, even for relativistic cases, with p being the relativistic momentum. That means when particles go really, really fast, these formulas would lead to less energy, sometimes almost half as much being accounted for after a collision. Well, if that's true, why haven't particle accelerators blown up or at least produced a zillion more particles than we actually observe? David argues it's because what's actually conserved in these equations isn't energy per se, but something called the temporal component of four momentum. That's a mouthful, but it's basically a chunk of math that, according to this view, tracks with observations but isn't exactly the energy we're used to talking about. Okay, practically, what does all this mean for you and me? Honestly, most of us aren't smashing subatomic particles daily. Instead, the big questions come in when we're trying to understand the deeper universe. Are these strange ideas a possible reason for why energy appears to be missing in galaxy dynamics? Or why cosmic expansion seems to be, well, on overdrive? Maybe. David suggests that energy non-conservation, if it happens, could feed into what we call dark energy. Similarly, matter and antimatter could behave differently under these formulas, maybe helping make sense of missing mass or dark matter. These are still open questions, though. Nobody's saying we should rewrite the textbooks tomorrow. Also, if the way we calculate energy in quantum mechanics is off by a factor of 2, that might affect things like how atomic spectra are explained, or how electron spin-orbit coupling works, a long-standing puzzle in physics. But let's be real, not everyone will be convinced. There are obvious reasons to doubt these alternative formulas. ESR MC2 has worked really well in experiments for over a century. If we accept the new view, a bunch of other things would need reworking, and not everyone will agree that's justified. So, should you toss out what you learned in physics class? Nope. This is just a horizon-expanding thought experiment, but it's worthwhile. If you're curious about how laws of nature are built and why some things are taken as absolute, David's paper is a reminder that sometimes competing views are out there, and that as scientists, we need to keep poking at the foundations. Science is a journey, not a final destination. Thanks for joining me today. Remember, you can check out the full paper by David Lush if you want to see all the details and equations for yourself, because, well, some things really need to be seen with your own eyes. And as always, this is just one perspective. Don't take my word for it or anyone else's. Let yourself be curious. Until next time, I'm Richard Price, and this was In Depth with Academia. Stay curious, and I'll see you soon.